We're talking about reinforced concrete, but before we do that, let's review what we know about creep. When we looked at failure modes earlier this term, we saw that one of the failure modes is a thing called creep. And creep is plastic deformation. So we talked about yield failure. First of all, we looked at our stress-strain diagram and we said, okay, when something yields, it goes past its elastic limit and it goes into plastic deformation. So that means it's no longer elastic, it's not coming back, it's going to keep stretching. That's a yield failure. Creep failure is a yield failure that happens real slowly over a long period of time under constant stress. And concrete is susceptible to creep. So here is a photo of a bridge that is experiencing creep in the middle of the span. Here is a building with a concrete slab that is experiencing creep in the middle of the span. An issue is thinking about what we're doing when we pre-stress a beam or we post-tension a beam. We're putting positive camber in that beam so it will kind of bow upward so that when we put a load on it, the bottom of the beam will be bent downward. The bottom of the beam will be in compression, which concrete likes, and all will be well. Well, when you start to get creep, that sagging can counteract the good things that the pre-stressing or the post-tensioning did. And so your engineer will be calculating what is the likelihood of creep, how much of it will happen, and they will calculate how to offset the effect of the creep so that it doesn't overcome the good work that the pre-stressing and post-tensioning does. That's part of civil engineering, which is an interesting field. Well, we're talking about reinforced concrete. So concrete is bad in tension and it cracks at the bottom. That's why we put in rebar. Also, as the beam is bent, it experiences shear in the middle of the beam, and we saw on a previous day that when things shear, they tend to shear at a 45-degree angle, and so engineers and then contractors locate their reinforcing bar to counteract those 45-degree shear impacts. The most efficient way to handle that is with rebar, reinforcing bar, that's bent at a 45-degree angle, because that is exactly at 90 degrees to those shear lines. However, contractors often put in vertical stirrups of rebar spaced closer together where the shear is going to happen, because it's just easier to make. You know, that 45-degree is kind of sophisticated and you have to be careful. These stirrups, you can just bend a bunch of 90-degree angles and it's easier and therefore more economical, because we pay for labor by the hour. It's interesting to think about how concrete is brittle and steel is ductile, thinking back on a previous day when we talked about being brittle and ductile. And what we said then was that concrete is a brittle material, which means it gives no warning of impending failure. A brittle material just goes from fine to totally broken. Dry spaghetti, concrete, brittle materials like that, no warning. Ductile materials like steel will yield first. They will have a yield failure, so they've passed their elastic limit. they go into plastic behavior, so now they're stretching out and they're not going to come back. They're in plastic mode, and that means you get large deflections, you get warning of impending collapse, so you know something is wrong before the thing totally falls apart. And the reason for talking about that here is just to note that engineers are aware that if they put in too much rebar, then the rebar will hold up fine. The concrete, the brittle material, will be the first thing that fails, and it will just totally come apart with no warning because it's a brittle material. The steel, it's a ductile material, and if you do not use enough steel, well, that's bad because your beam will fail by sagging too much, but at least you'll know that that something is happening. So engineers carefully calculate exactly how much reinforcing bar should they put in a given beam. Then, to review what we looked at in the previous set of slides, here are some drawings from Lise Crutcher Lewis of the construction of the LCC downtown campus building. Here is a floor plan at the second floor, level 2. This is the reinforcing plan now, so they're showing us where the rebar will go in place. And notice again here are the bubbles for the grid lines, DEF, 1, 2, 3, and so forth. Here's another plan showing, so this one just showed a glimpse through the concrete. Here's a plan showing all the rebar and lots of details. And this would have been drawn by a drafter. Then here is the actual rebar in place, and I don't know if you can see, but these bars are attached together with these ties. Then some more detail about the rebar. And a photo of the rebar underneath, and then you probably recognize these. These are the conduits for the post-tensioning cables. A detail showing rebar, but also the post-tensioning again. And here is a close-up of the rebar that has been formed at a 90-degree angle. And from what you know about moment of inertia, you know that this 90-degree angle is adding stiffness to the shape of the material. And an engineer has calculated this and has figured out where to put these stirrups for reinforcing the edge of the slab where the shear will be the greatest. And here's the building under construction where we saw all that happening, and here's the finished product. And if you go to downtown Eugene, this is what you will see. By the way, this stuff on the front has nothing to do with concrete, but I'll just point that out in case you're wondering. This is a solar hot water, solar water heater called an evacuated tube heater. We'll talk about that in sustainable buildings class if you're interested.